Previously, we looked at the linear regression and logistic regression algorithms. Now, we are going to apply this in solving a real life problem. Let's come back to this dataset we got from the Cengage.com site. That's specifically the health dataset under the data for multiple linear regression rubric. We have x1, x2, x3, x4, x5, which we discussed last time. And we are going to work particularly for this exercise with x1 and x2. Now, feel free to work with the other variables and see how, for example, using x4, you could predict x1. For now, we're going to use x2 to predict x1. Looking at the CSV file we downloaded, we have this first column x1, the next x2, the next x3, x4, x5, which contains 53 data points. Now we're going from this 2 to 54, so we have exactly 53 data points we're working with. So we're basically going to use this x2 column to predict x1. We shall then import numpy, pyplot from matplotlib, and then pandas. We shall use numpy for calculations, that's for matrix operations, pyplot for plotting, and pandas for extracting the data from our CSV file. Now, let's consider this function prepare dataset, which takes in a file name and outputs the input and output for the machine learning model. So we could start by getting this data from our CSV file. Now we've named it health.csv, so we have a data frame. We could say we have a data frame which is equals pandas.read.csv, and then we'll put in the file name. So yeah, we have this file name. Now if we print this out, we have data frame, and there we go. So we could run this, and then we could say we have prepare dataset, put in the file name health.csv. So this is exactly the data we have from our CSV file, which we could visualize easily, very quickly here. Then we could go ahead and extracting data and put in two lists. So we have x1, x2. We could declare this empty lists. We have for items, for item rows in data frame dot iter rows x1 dot append rows, or rather row x1. So this is how we take x1 and put in x. That we have this x1 from here, and we put it in this our list. So we repeat this for x2. We could copy this and repeat for x2. We have this, and there we go. So we could print this out so we could see exactly what it gives us. So we have x1, which is equals this x1, then we have x2. Then we take away this data frame, we print it out, and then we run this. So we see here how we have x1 in this list and x2. Now let's go ahead to fit this in a list x. So let's declare x and y. So we have now our outputs. So we have this, and then we have this. So we have this input x, which is going to get into our model, and the output y. Then for I in range, the length of x1, we'll take x1 or x2, but in either case it gives us 53. For I in this range, we have x that append 1 comma x2 I, because we're dealing with, we consider x2 as our x, and then we have y that append x1 I. Now we could output this as numpy arrays. So we could have x, then y equals np.numpy array y. So with this, we could print out x and y. So we have this x, y, and there we go. We see here that we have this x, which is made of the bias column, and then the column made of the actual values we got from our CSV file. We are obtaining an error as here we have the same values everywhere. So looking back, we see that we did not do this correctly. And then we have this, we run it again, and we have now our values. That done, looking at our data set, we have our x, which gets values which are somehow in the range 75 to, for now, 196. So looking at these values, we could take, or we could divide through by 100 or say 200. So if we divide all through here by 200, we're going to normalize the values for our inputs. And this is a pre-processing technique which is going to pay off when we're going to be training our model. So for now, let's take this off, and there we go. Recall that from linear algebra, we have a normal equation which we could use to directly solve for the best possible values for theta 1 and theta 2. As in this case, we're looking for theta 1 and theta 2, such that when we multiply, say, this first row of x by theta 1 and theta 2, and add them and add these values, say we have, for example, 1 plus theta 1 plus 78 plus theta 2, we have a value as close as possible to 8, and we'll do this for all the data set. So basically, our normal equation is given as theta 1 theta 2 equals x transpose x, that's the transpose of x, times x inverse times x transpose times y. So with this, we can automatically find the best possible values for theta 1 and theta 2, which will help in getting a model which is as close as possible, or which represents our data set the most. So this is the formula which we get from our linear algebra course. Converting this into Python code, we have this inverse function is gotten from the linear class of our numpy package. So we have this, take this away, and then we could print out our theta 1 theta 2. So here let's take this off and we'll run this. So we'll see clearly here that when theta 1 is 8.71 and when theta 2 is 5.07 times 10 to the negative 3, we are able to represent this data set in the best possible way. Now, after calculating theta 1 theta 2, we could output it. So here we have theta 1 theta 2, and then collect it this way. So we run the cells and we have this. So this is values for theta 1 theta 2. Could take this off. So now we have theta 1 theta 2. Then let's run this. First, let's start by explaining this piece of code. Basically, here what we're doing is we're plotting our values, or we're plotting the values for our data set, and we're plotting using the best possible values for theta 1 theta 2. We're plotting a line which best fits our data set. So let's plot this, and this is exactly what we have. So this is our data set x2 x1, and then this is our best fit line. Let's explain this piece of code. Now we kind of read from our data set. So this is like our data frame, and then from here we have data frame. So we have item and row. We get it from our data frame that's iterating through all the rows, and then we collect x2, collect x1. From there we have x, we have y defined. Now the value of y is gotten by using our theta 1 theta 2. So we have theta 1 theta 2 0. The first, that's 8.71 times 1. So we could also do this times 1 to be more precise, which is not different from what we had initially. And then we have plus theta 1 theta 2 1, that is actually 0.17, which we had, times I. So where I is taken in the range 0 to 30. So with this, we are able to generate y from getting all values between 0 and 230. We generate y using theta 1, theta 2, and then we kind of like plot the line, and we see clearly how it fits in our data set, or it represents our data set, such that if we have some new value, say for example 55, we could get the value for x1 using the best fit line. Now that we've seen how to solve this using our normal equation, we are going to use the machine learning technique we saw in the slides. But you may be wondering why we have to go through that, whereas we could use this simple formula to get this best fit line. One of the major disadvantages of this method is that when x has so many features and data points, the calculation of the inverse becomes very computationally expensive. Let's look at the implementation of the linear regression algorithm. We could start by this setting where we make sure all random values always remain the same, so that we could do testing and debugging very easily. Then we have the xy gotten from this data set. So yeah, we could take this off because we've done this already. Now we define the number of epochs. That's the number of times we are going to repeat the gradient descent algorithm. Then the learning rate 0.1. We define the batch size to be x.shape 0th index. Now let's calculate x.shape from here. We have x.shape. We thought that this is, so we could take this. Then running this, we have this shape. So basically what we're saying here is our batch size is going to be 53, since we've got an x.shape and taking the 0th index. That said, we initialize theta to be this random value with shape the first index of x, which is in this case 2, and that's simply because we are having a 2 feature x. Remember when we plotted x, or when we printed out x last time, like we had this, so print this, we had this 2 feature x with 53 different data points. So let's take this off, and that's exactly why in this case we need to actually define theta such that it's has values theta 1, theta 2, since we're working with this 2 feature data set. Now we could initialize our losses. This is going to be a list which is going to accumulate the losses over time, so that we could plot loss versus epoch plot. Now we have our gradient descent algorithm, which is clearly done here. Now let's get straight away into this algorithm. We have for I in range epochs, that is, we'll go through 10 times gradient descent algorithm. That means we're going to repeat this algorithm 10 times. We initialize our loss batch. I could better define it as epoch loss, because there's a loss of this epoch. So we have epoch loss. At this level we have epoch loss, and here to epoch loss. Now we have for B in range 0 len x batch size. This may seem a bit confusing, but let's take a simple example this way. This syntax simply means we are going to move from 0 to 53 while taking steps of 10. So normally when we do this, see we go from 0 to 52 now while taking steps of 1. So by default is 1. Now when we do this, say 10, we have this. So that's it. Now that said, we want to break our data set into mini batches. So that's why we have x from B to B plus batch size, and so on and so forth. So that's why we repeat this throughout. Now let's plot out x, and you could find this difference. So let's say, for example, print x. Let's say this is a B. So recall that when having this as 10 or going through these 10 steps, B starts from 0. So let's say this is B, as in this case we have this B. up to b plus the batch size. So we're supposing that we're dealing with a batch size of 10. Now let's print this out. We have exactly this. Let's print out x so we could see exactly how this works. So this is, let's create a little space here. So we have something like this. So now we see clearly here that we have the very first 10 elements of x which is selected on this. Now the next time we come in, we're not wanting to say, for example, 1 1. We may feel like doing this, but this is actually wrong, as our aim is to get the first 10 and then the next 10 and so on and so forth up to the last value. So in this case, doing this is going to just give us the first 10, the next is going to shift by 1 and then go to the next 10 and so on and so forth, which is wrong. So what we want to do here is go to 10. So normally we should have this. So we'll see here that we start from 149, which is exactly here. So we'll start from this 11th term to the 20th term. So that's exactly why at this level we're doing this. That's exactly why we're doing this. We're having this b and b plus batch size up to this y b plus batch size, because we're dealing with a particular mini batch of our total data set. Now for this problem, we defined our batch size to be 53. So in this case, we're talking about batch gradient descent, and if we want to convert this to a stochastic gradient descent algorithm, we'll simply change this batch size to 1. So that's going to be simple. Or if we want to change it to a mini batch of say 16, we could have this. So as simple as that. Now let's take this back to what we had initially and we continue. So we've seen how we could cut our data set into chunks and work with those chunks. So we're gonna have for b in range this, as we'll go through all our data set once. We have d theta. This d theta represents the partial derivative of the loss with respect to the thetas. So we had seen this already in the slides. We have now theta minus equals. Recall that this minus equals here. So if you have, for example, e equals 0, e minus, so here we have e minus equals 3, and then if we print out e here, we're gonna have minus 3. So this, or if we take, let's say for example 5, here we're gonna have 2. So this is the same as saying e equals e minus 3. So it's the same. So actually what we're doing here is we're applying that gradient descent step where we have theta equals theta minus alpha, or minus the learning rate. So this is the learning rate times the partial derivative of the loss with respect to the theta. So we could take this from here and put here, it doesn't change much. So we have alpha times this, which is a partial derivative with respect to theta. Now notice that we could even take this off because this is a constant. Now taking this off wouldn't change much while doing the training, but for us to maintain the formulas we've been working with, let's just use this. And clearly we see that this particular values, this 2 divided by the batch size or 2 divided by m, doesn't really change much, because say we have a learning rate, if we have a learning rate of 0.1, and then the 2 divided by m is equals 0.01, having learning rate times this, that is having this times 2 divided by m, is the same as just choosing the learning rate of 0.001. That is, if we take this off and choose a learning rate of 0.001, we'll have the same output. So many times we will not need to put that term, so we could even take this off. Now that said, we have updated our theta. That is actually the gradient descent step. This is the gradient descent step, very important step. Gradient descent step. Then we calculate our loss. So we have again the y minus x times theta. We had seen this already in the slides. We have this formula and then we do the square. So we have np dot square and then we calculate the mean. This mean is the same as doing the sum of all the values divided by the batch size. So basically this mean comes to help us get this very easily. Now we attach this to our epoch loss, or rather we add this to our epoch loss, simply because as we move through this for loop, we want to make sure we keep on adding the loss or the losses. So if we pass through this only once, we're going to do this only once. If we pass through this many times, we're going to add this up so that for a particular epoch, we have the loss. And then finally, when getting out of this loop, we could have, or we could append this loss for that particular epoch into this loss list. And then once we have this list, we could later on plot a graph of loss versus number of epochs. So that said, let us run this. We'll find that we're having a model which is diverging. So it tells us that our learning rate is already large enough. So it's too large, it's larger than what we expect. So we could turn this to 0.01. I'm running again, it's still very large. Turn this to this. This is still very large. Let's continue reducing. So we'll find that finally we get the learning rate value, which is gonna permit us get some convergence. So this is the same as 1. So we have 1, 2, 3, 4. So we have 1 e negative 4. So that's basically it. Now we could run this over for many more epochs. So we'll take this to 100 and we'll have this value. Now notice that the more we shall be running it, the more the values for theta is going to be approaching this best value. Or we are taking this off. If we run this, say we have this, let's print this out. So we're trying to get to these values sometime. So let's add the number of epochs, take this to 1,000. After this, we'll find this value, take this to 10,000. You notice that this is going to be approaching 8.7 the more we increase the number of epochs. Now we take this to 100,000. Takes a while. And then finally, this is what we have. We have this 5.67. Our loss has left from a value of around 8 now to 3.55. That's the loss at the end of the training. And then we could add again this. So we have this. Let's multiply this by 5. So we have 500,000. Now we've gotten again even closer to the 8.7 mark. So we're kind of like approaching the ideal value as we keep on training. Now let's do a little modification and see how that modification is going to help us find this ideal value more efficiently. Let's get back to our data preprocessing. So let's divide this by 200. Now we have this. Anyway, take this off. I'll run this. Now after doing that modification, we have this values for theta 1, theta 2, and that's the ideal values. Now notice that because of this pre-processing, we kind of now like with a learning rate of negative of 0.1, which we couldn't do previously. We had previously to work with at least that's a learning rate less than 1 times 10 to the negative 4 for us to be sure of convergence. But now with this, that's 0.1 practically, we're going to converge this data. We're going to have this nice results. And also the number of epochs have left from 500,000 to just 5,000. So with just 5,000, we are able to converge or to feed our model with our data set very easily. So let's run this. So you see that it doesn't take much time this time around, simply because we've pre-processed our data appropriately. And this tells us that pre-processing of our data is very important, because imagine we had a data set of say a million data points, because in this case we were having just 53 data points. Now working with a data set of a million data points and having to pre-process like this will save us so much time. So for our assignments, you could, instead of working with just x1, x2, you could work now and see how x2, x3, x4, and x5 actually can be used to predict the value for x1. And don't forget to pre-process your data.